Okay, guys, so we have the next one. It's the same problem. Everything's the same. I'm not going to read the whole thing again. The other video was already too long, so this one's going to be a lot uh, shorter. And again, the text is the same. The difference is the question, right? So we have that the system displaces 0.59 meters horizontally, and we know that is before coming to rest. Now we need to find the speed of the 7 kilogram block just before it collides with the 3 kilogram block. And again, this is all collisions, right? This is all collisions. So before it collides, don't forget that for collision we have a before and also an after. This is what we have to focus on. Okay, I'm going to copy the given. I'm not going to do this again. It's a lot. We have the same, right? The question will change. But over here, we'll have the same stuff. Okay. So we have the given, and before we write down the question, we have an inelastic collision. So, because they stick. And we said that we cannot use this table, just like that, right? If we have net external forces acting on the system. The cool thing is that for the previous problem, we already included that external forces because it was friction. So now we can actually use the collisions definition, right? We have an inelastic for inelastic collision. So inelastic collision, because they stick. I know that's not the right definition. It would be the kinetic energy, internal kinetic energy is not conserved, but that's okay. Inelastic collision. We have that I'm going to write the whole thing, okay? Mass 1 times velocity 1 plus mass 2 times velocity 2 before the collision, or we use the letter I for initial, right? Before the collision. This represents the collision, right? They collide, and that is mass 1 plus mass 2, right? Because they stick times the velocity final. That's why I said I'm going to keep this notation, because we know from the previous problem that the velocity final is 1.64 meters per second. That is from the previous problem. So now all we have to do, well, first of all, let's talk about the velocities, right? So we're looking for velocity 1 before the collision. That's what we're looking for. This one. And we know that the velocity of the second mass, right, is 0 because this one was at rest. It was somewhere here. This one is at rest. 3 kilogram block. Rest. And mass 2 is 3 kilograms. Therefore, this is 0 meters per second. If this is not moving, this mass is not moving, it has no linear momentum. So we cancel this one. Cross it out. That we have m1 v1 before the collision is equal to m1 plus m2 times the final velocity. And now we're only one step away from final velocity, right? Because we're looking for the initial velocity. Well, velocity of mass 1 before the collision. So we divide this by, oh, wait, no. It was over here, right? We divide by mass 1. We divide by mass 1. This cancels mass 1, so we have velocity 1 initial before the collision equals the sum of the masses times the final velocity divided by mass 1. Super simple. Again, we can use this now because this velocity, this final velocity, we found by using non-conservative forces, okay? So that's why for the second question, I can use the inelastic collision definition, because this final velocity has, I guess you could call it, embedded in it the fact that there was a force acting against it, right? This final velocity has friction included in it, and we showed it here, right? This is the friction stuff. So now we just substitute velocity 1 initial equals 7 kilograms plus 3 kilograms times 1.64 meters per second. And I am not going to draw this line by myself. Why bother? And mass 1 is 7 kilograms. Let's try that out. Although I could use this, now if I were doing my question work, I would keep the whole number, but I said round to the nearest hundredth, so I'm just going to pick 1.64. So we have double parentheses 10 kilograms, so I know that's 7 plus 3 times 1.64 divided by 7. 2.34, I think it's at round to the nearest hundredth, right? 2.34, that's what I'm going to pick. So velocity of mass 1 before the collision, oh that's ugly, is 2.34 meters per second. That's simple. Again, this one was simple because we already did all the work, well, most of the work over here by including the fact that we have a non-conservative force, right, for the energy. Now, just for fun, let's see if what we said is true, right? We said that for for inelastic, the internal kinetic energy is not conserved. It changes, right? So the internal kinetic energy before the collision for this one, we're doing this just for fun, would be, since the mass 2 is not moving, before the collision would be 1/2 mass 1 times velocity 1 squared initial, right? So let's see what that is before the collision. We're doing this just for fun, because if we were to get the same kinetic energy, we did something wrong. Mass 1 is 7 kilograms times the initial velocity, which is 2.34 squared. So that's the kinetic energy before the collision, right? Again, if I get the same number, I'm going to be concerned. And so, oh, wait, before I do that, right? So the kinetic energy after the collision would be 1/2 mass 1 plus mass 2 times the velocity final squared. This is the energy we use for this problem, right? This is because we were concerned, we wanted to find the velocity right after the collision, so that's what we used it on this side. So let's see, this has to be less than 19.16. So that'll be 10, right? 7 plus 3 times 1.64 squared. Boom. 19 to 13. So this is, as a matter of fact, an inelastic collision, as the internal kinetic energy of the system was not conserved. So there you go.